It's my great privilege to introduce our speaker for today. This is the Mechanical Engineering Seminar Series. So we have today speaking to us Matthew Eisaman, who is an Associate Professor at the Yale Center for Natural Carbon Capture.
The slides disappeared right as you started. I don't know why.
And also the Department of Earth and Planetary Sciences at Yale. So Matthew works on a variety of problems related to oceanic carbon removal, and including he also has a startup that works on carbon capture and carbon removal technology. Without further ado, welcome Matthew. We're interested in hearing what you have to tell us about carbon capture.
Great. Thank you. Thanks for the invitation. I have this microphone on, not for this room, but apparently for Zoom. Feels like overkill for this one. Yeah, so maybe I'll start. This talk, I'm going to talk some about the research that's going on in my lab, and then also some about the commercialization efforts at EB and how they feed into each other. And I understand this mechanical engineering department, not everyone is thinking about carbon dioxide removal all the time, so I'll try and give some a little bit of a slow introduction in places. So there should be something for everybody. Some parts will be an overview, so don't be insulted if you know some of those pieces already. Yeah, so first, just the need for carbon removal, which I think a lot of people here probably are familiar with, but especially when the IPCC a couple of years ago came out, and there was consensus within the IPCC that to meet our climate goals, in addition to decarbonization, we also need on top of that, like multiple gigatons, multiple billions of tons of CO2 removal per year, which is a huge number. So at this point, then I think people realize that this, in addition to decarbonization, this is something we need to start pursuing. And so, the example being looking at different scenarios and what average increased temperature change results from those different scenarios, right? So 3 degrees Celsius or more if we do nothing, and then all the scenarios basically that get us to 2 degrees or below at this point involve decarbonization in addition to something like 5 gigatons of CO2 removal by 2050 and something like 10 by the end of the century. And in principle, if we had millions of years to wait, we could just let the Earth's regulatory mechanisms do this for us, right? So in the geological history of the Earth, carbon dioxide concentrations have been much higher. And there is a natural regulatory mechanism for dealing with that called the carbonate silicate cycle, where increased carbon dioxide concentrations in the air increase the temperature, and the CO2 concentration in rain. Both of those increase the rate at which alkaline minerals, silicate rocks weather. And in those reactions, carbon dioxide is bound up as bicarbonate that goes into the rivers and the ocean. So basically CO2 is then the rate at which CO2 is stored in the ocean as bicarbonate increases as CO2 increases. So it's a feedback mechanism. Unfortunately, that takes millions of years to operate. And so we're trying to solve a problem on human timescales. So what we want to think about, that a lot of the research I'm focused on is how you can use technology to kind of nudge these natural systems forward and speed them up to some degree. And so then when you decide you want to speed up natural systems, it makes sense to look at the carbon cycle and where you might do that. And I think in the end, solving this problem will involve not just oceans, which I'm focused on, but also soils and forests and all of the different pieces, which are all interacting. But when you look at this, you can see the ocean is the largest store of carbon in that system other than continental crust. So it will almost certainly play a large role in the suite of solutions that we all develop. And so the Yale Center for Natural Carbon Capture is focused really on enhancing natural solutions. So that includes ecological and biological capture. We have a lot of experts on measurement and verification for soil carbon, geological capture, such as enhanced rock weathering. And then I focus on ocean capture. And then also something I know you all are focused on here, carbon capture and reuse and utilization. And one of the key missions of the center is to do the fundamental research and fill the knowledge gaps in the field, but in addition, translate those out into the world to help actually deploy some of the solutions that we develop. Okay, coming back to the question of why I'm focused on oceans. If you took all of the CO2 that we need to remove by 2050 and stored as oceanic bicarbonate, that would only increase the dissolved inorganic carbon in the ocean by 0.1%, which is to say, you can make a significant impact on the climate problem, but only a small perturbation in the ocean system, which is a good thing. And this makes sense just given, if you look in the geological history of the CO2 concentration and its variation in time, the oceans are playing this huge role in pulling CO2 into and out of the air. So I'll talk about two things today: the research in my lab, which is focused on a lot of the scientific questions in the field, and then at the end, I'll give a little update on Ebb Carbon, which is a startup company that's commercializing these ideas. And I think these arrows are important in trying to commercialize these technologies. Through that effort, we learn a lot of the important questions that we need to answer to actually scale these solutions. Okay, so the first question, if you're not, for people who are deep in the carbon dioxide removal space, they've sort of internalized all this, but coming from outside, you may say, how in the world who would invest in a company, or how could you have a company dedicated to carbon dioxide removal? How does that even work? And this is because of this newly emerging voluntary carbon removal market, is basically what it's called. And so you have companies like Microsoft and Stripe and others who have made net zero commitments. And to satisfy those commitments, they need to purchase active carbon dioxide removal from the air. And the supply basically doesn't exist or didn't exist. And so they have made advanced market commitments. So the Frontier Fund, these companies pooled $1 billion saying, we will make advanced market commitments to purchase carbon dioxide removal. That advanced market commitment then spurred the formation of many startups working in different areas of carbon dioxide removal, including Ebb. And just to make a point that up until 2020, people talked about avoidance, so CO2 avoidance, and that you would have an offset or a credit where by avoiding an emission here, I would allow someone to emit somewhere else. That results in 1 ton still being emitted. What we're talking about now is shown on the right. So after 2020, it's not carbon offsetting, it's really carbon dioxide removal. And so that is what gets you to net zero. So yeah, you can see my cursor. Also, am I standing in the way for, let me just, yeah, I guess it's the way the room is set up. Let me stand over here. That's probably better. That actually gets you to net zero, right? So now I'm actively removing from the air, and so the net emissions in that case is net zero. And these are carbon dioxide removal, not offsets. If you want to learn more about the ocean-based carbon dioxide removal space, this National Academies report is a good place to start. And in there, I will talk today about ocean alkalinity enhancement and using electrochemistry to generate that alkalinity. But there are many other approaches, including biological ones that are growing seaweed and sinking it, artificial upwelling, iron fertilization. So this report's a great place to start, and they outline what they see as the research agenda needed to answer the outstanding questions and determine which of these approaches, if any, should be scaled. I think now in the field, we're at the point where we need to figure out, what is the cost, what are the co-benefits of each of these, which ones could scale, so that we're ready to scale the right ones soon. We're also working on, we just released this guide to best practices for alkalinity enhancement, which is kind of analogous to the ones that exist for ocean acidification. So just for the research community, for people getting involved. I was part of one chapter, but there are many chapters on different topics, like how you make carbonate chemistry measurements, monitoring, reporting, and verification, and so on. So if you're interested or getting started in the field, it's a good place to go if it's already online at the as a preprint at that link. And so here's the part, I know, this is not an oceanography department. So some of you may know what I'm about to talk about for the next few slides, but I'm told that people like being told things they already know, and especially professors. So they definitely like that because it makes you feel smart. So bear with me. And so I want to talk about, I'll use the phrase ocean alkalinity enhancement. And even when you talk with oceanographers, they sort of disagree a little bit about some of the details, like what is alkalinity? It's actually straightforward, but I just want to go over it. So first, a primer on seawater chemistry. What do we care about for what I'm going to talk about? Well, one is the dissolved inorganic carbon concentration, called DIC. That is the sum of the dissolved CO2 gas, the bicarbonate ion concentration, and the carbonate ion concentration in seawater at pH of around 8.1. About 90% is bicarbonate, about 9% is carbonate, and about 0.9% is dissolved CO2 gas. And yeah, that book cited at the bottom, also like a great thin little paperback that's nice if you want to think about carbonate chemistry in the oceans. The other thing we care about is, and you'll see that concentration is about 2.5 millimolar and of dissolved inorganic carbon. And then we also care about the sodium and chloride concentration, which is about 0.5 molar, because that's what we use that salt and convert some of that salt into acid and base in our pH swing reactions. Okay, so the carbonate buffer system is the focus of what we work on and what we manipulate to do what we're doing. And these equations, each have an equilibrium constant. This first one is just Henry's law, saying that atmospheric CO2 is in equilibrium with dissolved CO2 in the ocean. The second one is relating the ocean surface dissolved CO2 concentration with the bicarbonate ion concentration. And then the second relates bicarbonate to carbonate. But the key point is that you see protons mediate each of these, right? So pH controls what the relative fraction of bicarbonate, carbonate, and CO2 are in the buffer system. So some of you may be familiar with this curve, where this is plotting the fraction of dissolved carbon as the different species as a function of pH. So the oceans are typically sitting at 8.1. And so that's sort of the peak of the red bicarbonate curve, right? So most of the dissolved carbon is bicarbonate. And what we can do with pH swing and using electrochemistry to make acid and base from salt is you can make it more acidic and shift all of the DIC to be dissolved CO2 gas, which then, if you want, you could strip out of the solution. And you can shift things to make them more basic, then you're shifting toward carbonate. And I'll go over a few schemes for how you use those pH shifts to use the oceans to remove CO2. Okay, so we'll talk also about alkalinity, ocean alkalinity enhancement. All it is really is buffer capacity. It's just the ability, it's resistance to acidification or resistance to pH change upon addition of acid. There are other ions involved, but it is mostly what I've written here. So the bicarbonate ion concentration, 2 times the carbonate concentration because the double charge, hydroxide, and then minus the acid concentration. And so what we have then, what we want to solve for is the state of this system. It's 5 variables. PCO2, so the atmospheric carbon dioxide concentration, carbon dioxide concentration in the surface seawater, bicarbonate, carbonate, and pH. We have three equations constraining them, which are the equilibrium constants. And so we have 2 unknowns, so we can measure any 2 and solve the system, or any combination of the 2. And so in practice, these combinations are what we often measure. So we have total alkalinity, or TA, and we have DIC, or dissolved inorganic carbon. So in practice, when you're making oceanographic measurements of the carbonate chemistry system, you measure any 2 of pH, so that's directly H+, PCO2, so that's just the atmospheric CO2 concentration. That's pretty easy to measure with an IR CO2 sensor. PCO2, which is, DIC, and the way you measure this is you acidify the seawater, strip out the CO2 as gas, and measure it with an IR sensor, or TA, and you measure that just with a titration. Okay. Okay, here ends the seawater chemistry overview. Okay, so let me talk a little bit about the main method that my lab and EbCarbon are exploring for carbon dioxide removal, which I'm calling here acid removal from seawater. But removing acid from seawater increases the total alkalinity. So this is a form of ocean alkalinity enhancement. And geologists don't like the acronym OAE because they think it refers to the oxygen or ocean anoxic events. So be careful with your acronyms. Okay, so the idea is we're taking a waste product, a brine stream that's going to the ocean. So think aquaculture, desalination plants, power plants that use it for cooling, and creating value out of that by using electrochemistry to convert some of that salt into acid and base, which we then use for CO2 removal. And so I'll go into a little bit, because I know some people here are a little deep into it. I'll go into some of the electrochemistry we use for this. But in short, you pass that seawater through an electrochemical system that is a stack of ion selective membranes across which you apply voltage. So you're moving those ions across those membranes to create an acidic and a basic stream. And the acid stream you keep on land and use that for other beneficial purposes that involve its neutralization, right? And then the alkalinity is mixed with the now slightly less salty seawater and returned to the ocean. So we've enhanced the alkalinity by removing acid. Right, so the effect of this alkalinity, I'll get into the actual chemistry in a second, but in short, you enhance the alkalinity, which pulls CO2 from the air and stores it as bicarbonate, just like the carbonate silicate cycle that I showed you. But we're using electricity to try and speed it up. What's actually going on in a little bit more detail is in the seawater, when you remove the acid, you shift that carbonate system toward the basic side, right? So you shift that first equation, you shift dissolved CO2 gas shifts toward bicarbonate, bicarbonate shifts toward carbonate. So now, and that reaction is basically immediate. So what we're returning to the ocean is enhanced in alkalinity, and because it's been shifted toward carbonate, it's relatively depleted in dissolved CO2 gas relative to where it would be in equilibrium with the atmosphere. So then when you return it to the ocean, over weeks to months, it's a slower reaction. It re-equilibrates. So CO2 from the air fills that depletion and equilibrium is restored. And this last equation is kind of important because if you just think of this one, then you think CO2 from the air backfills and it's sort of 1-to-1, but then there's a readjustment of the system. So some of that carbonate that you've shifted reacts with the CO2, and we'll get into it, but that's why it's not quite one mole of hydroxide gives you 1 mole of CO2. It's 1 mole of hydroxide gives you about 0.8 moles of CO2. Also, please ask questions along the way. So because of that sort of short-term, long-term separation, we can think about a co-benefit of local, not global, but local ocean acidification mitigation, where you imagine some estuary, maybe in the Pacific Northwest, that's doing shellfish aquaculture and is suffering from ocean acidification. And you say to them, what is the ideal carbonate chemistry? What are the ideal carbonate chemistry parameters to increase your yield for the shellfish growth? You know, maybe you're targeting an aragonite saturation state or pH value or alkalinity. So you dial in those parameters, you run this system to get it to that level. And then there's some rate of exchange with the open ocean. And so then you just continue to add alkalinity only to the degree to balance out that exchange. So you keep it at some desired target. So you're mitigating ocean acidification in that estuary, but you're still getting CO2 removal over that longer time scale. Yeah.
How long would it take for it to go back from mixing?
Yeah, so if you did this and then you stopped mitigating, it would just be whatever there would be the exchange rate with the open ocean, and then there's the CO2 removal. So probably the exchange rate is faster. So it's just whatever however long it takes for that to completely flush.
What order of magnitude would that be?
I think most of those, it depends on the size of the estuary, but I think you're talking about like days to weeks to months. Yeah.
Thank you.
Okay, so what I described to you, what we're doing, I'm going to try and put in a kind of a taxonomy to understand it in the context of other ocean carbon dioxide removal and ocean alkalinity enhancement approaches. So I think it's useful to think about the source of the alkalinity, how you process the source to get some type of alkalinity that you disperse, and then how you disperse it. So I just described using electrochemistry to go from brine to an aqueous alkalinity. And because it's aqueous and not that dense, you don't want to ship it over, you can't really use a boat to disperse it because it's too much energy. And so you'll mostly look at coastal surface dispersal. But you've probably heard about lots of other approaches to ocean alkalinity enhancement. So one of them is I crush minerals, I take minerals, I grind them, I spread them as a solid, which I could do offshore on the seafloor on the coast. Or some approaches use they take minerals, they grind them, and then they use those minerals in electrochemical reactors, and they can make solids or liquids. So these are I just want to say that like there are various possibilities of how you do this. And the alkalinity type, so for example, aqueous has the advantage, we don't need to worry about kinetics of dissolution. If you have an approach where you're crushing a mineral and you're spreading it, you need to worry about, do those minerals dissolve? At what rate do they release alkalinity? Do they fall out of the surface ocean? What we have to make sure of is that our alkalinity stays in the surface ocean longer than its time to equilibration. If it falls out of the surface ocean and is no longer in contact with the atmosphere, then we have some inefficiency, basically. Okay, so now we can think about, all I said was we're electrochemically generating alkalinity from brine. Yep.
So why do you grind the minerals so that they float on the surface to absorb the carbon dioxide from the air?
Yeah, we don't do that, but other researchers and other companies are doing that. And it's not as simple. So and actually that Academy's report goes into it. You could say, oh, I just want to grind to a really fine, very, very small size because the kinetics are better of dissolution and they'll stay in the surface. But it's counterintuitive. You actually get an agglomeration if they're too small and then they fall out. Yeah.
Eventually the carbonates will go to the bottom.
Yeah. Well, it's a question of, does it go to the bottom before it has time to equilibrate? And it depends on particle size and it depends on agglomeration rates.
And do you know if that's in practice commercially? Like, do people do this?
Yeah, there are some. So Project Vesta is a company who they're crushing, I think, olivine, and currently they're spreading it on beaches. I don't think they're doing anything off coast right now. Planetary Technologies, I think, I think they are dispersing solid magnesium hydroxide.
Thank you.
Yeah. Right. So just generally at a higher level, there are a couple of ways you can electrochemically generate this alkalinity from the brine. Almost all of them, actually, a reviewer comment, this is a preprint, and a reviewer comment was, you don't always need to remove the divalence. So that's fine. I think I've changed this figure since then. Yeah.
Hydrogen you generate.
Yeah, so we don't generate hydrogen, but those who do, I think, would then use that as a revenue or a product. Yeah, for sure. So you take a brine source, you do some pre-treatment to remove calcium and magnesium to some degree, because those will cause precipitation and scaling. And then you can perform electrolysis, which is mostly based at the electrodes, and you will tend to generate hydrogen and chlorine, or maybe oxygen if you have the right electrode. Hydrogen's useful, chlorine's not. You have to figure out what to do with it. And then you generally mix that alkalinity back with the desalted brine, return it to the ocean. That's how you enhance the alkalinity. What we do is electrodialysis. So that's a membrane-based approach. So here you have basically 2 electrodes and a separator or a membrane. And what we have are like 100 membrane pairs between end electrodes. So we actually do generate hydrogen and oxygen at the electrodes, but it's like 1 over the number of cells, or 1%. So we just combine them and bend them. It's negligible. But what we generate is aqueous hydrochloric acid. And so then one of the research thrusts that we're focused on is uses for that acid that end up in its neutralization at the megaton and gigaton scale of CO2 removal. Okay, this is the busiest slide, so I didn't have a chance to animate it. So this is bipolar membrane electrodialysis that we use to generate alkalinity from brine. So I want a few highlights. 1, 2, 3 different kinds of membranes, bipolar, anion, and cation. And those 3 together is 1 cell. So we have about 100 cells in a stack. The bipolar membrane is a laminated anion and cation membrane with a catalyst, a dissociation catalyst at the center. And then the applied voltage at the end is basically the energy to pump hydrogen and hydroxide against their concentration gradients. This is not water splitting, so it's not 1.23 volts or so. It's that pumping against its concentration gradient, which is about 0.8 volts for the typical pHs. So theoretically, this should have a lower energy consumption than electrolytic approaches. In practice, it's just less well developed at the moment.
Just from the solution of mixing energy to get rid of the mixing energy?
Yeah, it is simply pushing something against its concentration gradient.
20 volts seems high to me. You're talking about like 80 kilojoules per mole, but that's like mixing energy in solution should be like 2.5 kilojoules per mole.
Yeah, so don't forget that this is an acidic solution and this is a basic solution. So you're pumping into like pH 1 and 14. Yeah.
The
Yeah.
voltage required doesn't depend on the concentration.
It does. Yeah, for sure it does. Yeah.
Do you have like an over potential? Like what are how inefficient is this process?
Yeah, it's about 30%, you know,
Efficiency or inefficiency?
30% of the total energy is over potential at the moment.
Still pretty good.
Yeah.
70% efficiency.
Are these custom built bipolar membrane?
So right now we are doing everything commercial off the shelf, but we have kind of a 5-year plan for efficiency improvements and custom improvements, including stack design and membrane design. Yeah.
You know what the thermodynamic of like how much energy am I spitting into this versus if I were to compare that to other.
Yeah.
Like how does this stack up against other technologies in terms of energy per carbon dioxide being used?
Yeah. So fundamentally, thermodynamically, this is actually the same as air capture because it's exactly the same from a thermodynamic perspective. And so that is, 19, 20 kilojoules per mole of CO2. But in practice, I'll show some data at the end for a 100-ton CO2 removal per year system. We're between like 1 and 2 megawatt hours per ton. So for comparison, DAC in practice now is, I think, around 3 megawatt hours per ton. So it makes sense. It should be cheap. It should be less energy than DAC because we don't have the regeneration step, right? We have to kind of make the capture solution, the alkalinity, if you want, but then we don't need, once it's in bicarbonate, we don't need extra energy to release it. Just a few things to mention here. We do this sort of feed and bleed architecture, right? So brine comes in, and then we're pulling sodium and chloride out. So it comes out desalted. We bleed some off as a product that'll mix with the alkalinity and go to the ocean. And then we add brine so that these concentrations are always a constant. Same thing with acid and base, but in the other direction. Okay. And acid and base concentrations at the output, around half molar. We can vary it. We can go higher concentrations, but you start to get inefficiencies as we go higher. Okay, so what I talked about was just using this technology to generate acid and base. And there are multiple schemes you can use then with that acid and base to shift pH and remove CO2 from seawater. So the one that Ebb is pursuing that I'll talk about most today is this ocean alkalinity enhancement, where that alkalinity goes to the ocean, the acid stays on land. A separate one is what we originally called indirect ocean capture. Now people are calling it direct ocean capture, but if you talk to oceanographers, DOC is dissolved organic carbon, so they don't like that. Maybe CO2 stripping is a better name. So let me just explain the difference between these two, because I think it gets confused a lot. I think of OAE or alkalinity enhancement where the ocean is being used as a sponge. So you have seawater, you're extracting acid. This increases the pH and it increases the alkalinity. And then the acid we use for other purposes and make sure it's neutralized. Now we have seawater with increased pH and alkalinity. We release that to the ocean and let it equilibrate with air. So CO2 comes in, that increases the dissolved inorganic carbon. The pH decreases as the CO2 invades and comes back almost to where it started, but not the whole way. And the fact that it's 0.8 moles of CO2 per mole of hydroxide is why it's not the whole way. Because we've increased the DIC, now the equilibrium pH is slightly higher. But the total alkalinity stays elevated because CO2 invading does not change that. So we have increased the alkalinity of the ocean. We've increased the dissolved inorganic carbon content and slightly increased the pH. In the IOC case, I think you're cycling alkalinity. It's not increasing, and you're essentially using the ocean as a pump. So you first add the acid you made, that decreases pH and alkalinity. So now there, to that seawater, you extract CO2 because now you've shifted the carbonate system to CO2 gas. And by the way, the equilibrium partial pressure for 2.5 millimole is just 0.08 atmospheres. So this requires a vacuum stripper or some kind of sweep gas. When I extract CO2, I decrease DIC. So now my seawater is low pH, TA, and DIC. Then I take the base that I've made, add that increases the pH and actually increases it back above where it started because I don't have a buffer system anymore. And I've just restored the alkalinity. So now I'm back to where I started. So I haven't increased the alkalinity. So now I have seawater with high pH, like 10.3, and low DIC, and then that I release to the ocean and equilibrate with air, which restores the pH and the DIC right back to where it started because the TA has not increased. These steps where I release to the ocean, I need to do what's called monitoring, reporting, and verification, which is in this field of ocean carbon dioxide removal, one of the important kind of scientific efforts we need to lay a foundation to allow this to scale. Companies like Stripe and Microsoft who are purchasing these credits need quantitative bounds of uncertainty on that monitoring and verification. So I'll talk about some experiments in my lab that we're doing around those efforts. But notice that the MRV for both of these are actually the same. I've actually heard some people say, oh, this is much better because I just have to measure the CO2 I extract. That doesn't make sense because if I did that, I could imagine doing this for years and years and counting this CO2, and if it's never coming back from the air, I haven't done anything.
So on the left side, acid is a product. On the right side, acid is a reactant. I mean, can you just couple these two things into the same system?
Well, yeah, but the problem is this acid is made with this base, right? So if I take that acid and use it here.
You're using the base from over.
Yeah.
I got it.
Yeah. Basically here, in each case, here the thing I need to do something with is CO2, and there the thing I need to do something with is acid. And we've put some CO2 underground and mineralized it, but I think it's not clear actually at the gigaton scale if it's just easier to neutralize acid or if it's easier to store gigatons of CO2. We'll end up doing both, probably. Okay, so I'll start with some results from my lab, and then at the end I'll talk about progress. See how I'm doing on time. Okay. And so what we're really focused on is this MRV question, novel approaches. I won't really touch on those today, and then environmental impact, looking at impact on organisms as well. So first, for this MRV piece, some modeling of a large-scale deployment, and that helps us understand like what we need in terms of sensors and sensor networks. So in this paper, we modeled an OAE intervention that was basically like 0.5 megaton of CO2 removal per year in the Bering Sea. You know, the reason we chose the Bering Sea, one, is that the modelers we're working with are experts in a model of the Bering Sea. The other is the Bering Sea is actually a really good place to think about ocean alkalinity enhancement. It's basically like a giant bathtub. So it's going to stay in the surface ocean for long enough to equilibrate. And so if you look at these movies, you see exactly these two different timescales that I was talking about. Where here, this is the total alkalinity, and you see you get these sharp increases near the site of release. This is the CO2 flux as a result. And then this is the DIC increase, which you see is much more diffuse. So this CO2 flux into DIC is that slower equilibration equation, whereas that first one is just that immediate increase in alkalinity. And then you can look at snapshots of this to really understand the challenge of MRV. So imagine we said we want to directly measure with carbonate chemistry measurements the CO2 removal as a result of this intervention. The obvious thing is let's measure dissolved inorganic carbon, right? And so we can make a map of the increase. These are like ISO lines of dissolved inorganic carbon. So this is 0.5 micromole per kilogram increase and 0.2. And so what you see is the natural background is about 2000 to 2100, and we've increased it here by 0.2 to 0.5 micromoles per kilogram, which is below current instrument resolution, either benchtop or in the field. So that's a problem. What it would mean is if you wanted to measure in this example, either I'd have to restrict it to a narrower region nearby, or I'd need a larger alkalinity release for that location, or I need a different location that's more protected, right? So there's this advantage. If I do this in a protected estuary, I may have a better chance of measuring when we're still at a small scale. It's a little bit better story with pH. So this is just showing the surface area over which I can see various pH changes, and compared to the natural variability of 0.02 to 0.14. And so you can see with our current instrument resolution, like these actually could be detected over large areas. So with pH, we actually can make measurements over pretty large areas, but that's not solving, pH alone is not solving the carbonate system. You need two measurements. So what this means is, I think what MRV looks like for this kind of approach is first you make you make carbonate chemistry measurements as far away from the dispersal as you can until basically the signal to noise ratio is not good enough anymore. Then you use those measurements to constrain regional models. So in other words, you say the model must agree with these measurements that I made. And then you run the model in the case of the release, and you run the model in the counterfactual case where there was no release, and take the difference in the amount of CO2. Great, so that's how we ran those simulations. In the future, ideally what we want to do is be able to run those models many, many times, and then each time randomly draw from the distribution of input variables to get a probability distribution. Because what we really want to do to buyers is say, it's not that we removed 100 tons, but that we removed, maybe the distribution centered on 100, but it has this distribution, and they can decide how to discount the uncertainty of that removal. And so related to this, I think, if you think of measurement verification, you have a sensor network out to some distance where you can actually see the effect. You use those to constrain models, but also, in some sense, all hope is not lost, because the measurements and the sensor networks for MRV for alkalinity enhancement are different from traditional sensors. So a traditional oceanographic sensor is saying, like, what is the value of pH in space and time right here? And accuracy, I want to know the true value. For OAE, I actually just want a difference relative to the baseline. And it's conditional on many things. So it's basically saying conditional on the known rate of alkalinity release, what my model says that plume will look like, and the baseline measurements I made. Like, what is the likelihood that this amount of CO2 removal is due to this intervention? So that's an easier, more constrained problem to solve. It also means I think there's a lot of opportunity for new sensors. The constraints are different. Maybe we want cheap sensors that aren't as good because we just care about deltas. And then thinking about how to optimally configure those networks is something I have a student working on that right now. Okay, so related related to this, I I need to know how long I want to track the plume, right? So especially if I'm doing this measurement and modeling, if I know the equilibration takes 2 months, then I can say, okay, I need my measurements and model to be accurate out to 2 months. And so I need to know what the curves look like for CO2 equilibration. So for that, I think what we'll end up doing is kind of tiling the ocean with those efficiency curves. And so you just need to measure these for the seawater with the properties at your location. So some results from doing that at Flax Pond Lab in the North Shore of Long Island. So we pump, the lab, they just installed a new pumping system. So it's basically there's seawater flowing in these pipes in the ceiling, and you can just grab seawater from the ceiling and fill your tanks, which is great. So we have 2 6,000-liter tanks. One serves as control, one serves as experiment. And what we do is the control tank, we add nothing to, or we add maybe brine to. And the experiment tank, we dose with sodium hydroxide to a target alkalinity and pH, and then just let it evolve. And then we're kind of over constraining the carbonate chemistry. So we're measuring pH with 2 or 3 different sensors, including this is a collaboration with NOAA, PMEL, and University of Washington. So we take bottle samples of alkalinity and DIC and send it to them for analysis. We're measuring the atmospheric carbon dioxide concentration above the tanks, dissolves oxygen, temperature, salinity. So we're sort of overdoing it for these first experiments. I'll dive into some of the data behind this, but these are the efficiency curves I'm talking about. So basically looking at, on the vertical axis, CO2 removed per HCl extracted on a mole per mole basis, or in other words, CO2 removed per hydroxide added, right? And then over days. And so what you see is most of them are fully equilibrated after about 50 days. Everything except green, the surface is still. That green curve, we force airflow and bubble, so you can see it equilibrates faster. All of them are asymptotically approaching around 0.8 to 0.85. And this ratio that we expect from the carbonate chemistry parameters. And then these different delta pHs, the seawater starts in Flax Pond, it's about 7.9 pH. So these are like, this represents pH, starting pH of 8.7, 8.5, 9.3, right? And so how we get those curves, and the point here is now this could tell us, okay, for this seawater composition, we have these efficiency curves. And if we start understanding how it depends on airflow and air-sea surface area contact, then we can use oceanographic conditions to infer how long we need to be tracking those plumes for MRV. This is the suite of measurements that went into that, and I'm just gonna zoom in on the top half and then the bottom half. So we have temperature, which is just ambient in the room. Excuse me, PCO2, this is atmospheric in the room. Again, this is just as people come and go, it's going up and down. Seawater temperature, salinity you'll see is going up, it's evaporating over time, so all of our measurements are corrected for the salinity increase. Dissolved oxygen is a sign of biological activity. We actually bleach these tanks and then break down the bleach in UV filters. We're starting to study the effects of biology now, but we wanted to first have a controlled environment without it. On pH, you'll see the experiment tank in red starts high, and then it's decreasing over time. So you might say, there it is, proof of CO2 removal, but we need to show why that pH is decreasing. That's on the next slide. Total alkalinity, higher for the experiment tank, flat for both, that's good. A decrease in TA is a sign of precipitation, which would remove TA. Okay, so pH, TA, I just showed you, and then here the third one is DIC. So now you see the DIC is increasing, so that's confirming that that's the reason the pH is dropping. And then some of these are calculated from these measure values, but the PCO2 in the seawater, you see in the experiment tank is depleted relative to equilibrium to start, and then it is approaching equilibrium by the end. Aragonite saturation state, of course, starts higher in that experiment tank and then comes down. And then this is that ratio I just showed you. So these kinds of maps are what we'll need to start measuring for MRV.
Do you also track how much aragonite is precipitated?
I couldn't have timed that question better.
Okay.
I literally have pictures of aragonite about to show you. I did not plant that question, thank you. Yeah, so we need to worry about making sure we're not precipitating and understanding what those thresholds are. So we did one experiment where we purposefully increased the bulk tank pH to 10.3 to induce runaway precipitation. So here, during the addition, what you see is brucite in magnesium hydroxide. So if you do this and don't go all the way to 10.3, this will redissolve because it's undersaturated. But then if we go all the way to 10.3, after 3 hours, very, very cloudy. And if we take samples, this is samples in the water itself, so not scraping from the bottom. After 3 hours, we are mostly seeing magnesium hydroxide, but then somewhere around 3 to 24 hours after addition, it starts to be dominated by aragonite. And these are XRD images showing that, right? So you basically see these magnesium hydroxide peaks disappear and replaced by aragonite peaks. And so what's happening here is that magnesium hydroxide serves as a nucleation site for calcium carbonate precipitation. Okay.
That seems counterintuitive. I see the nucleation side of it, but then when you form magnesium hydroxide, it changes the local pH, which should steer it away from carbonate precipitation.
Well,
It should form technically much higher.
yeah, well, 10.3 is, there is room, I mean, you're super saturated with respect to calcium carbonate anyway. So it's always just kinetically limited. So even if the pH decreases once that magnesium hydroxide precipitates, it's still, thermodynamically, you should still have calcium carbonate precipitation. Yeah. Okay, so briefly, some updates and description of what we're doing at Ebb Carbon on the commercialization side. Ebb is based in San Carlos, California. Actually, we have two. We have a facility in San Carlos and one in Burlingame, and then we have our first kind of pilot project site at Pacific Northwest National Lab in Sequim. And we're at the stage where we just closed our Series A couple weeks ago. This is in our San Carlos headquarters. That's a 100-ton per year system. And Stripe is our first customer, so they purchased carbon removal for us that we're working to deliver on. And you know, happy with the investors and the partners we have, including NOAA and the Department of Energy. Our roadmap, step one is to establish efficiency and safety, which are partly the experiments I just showed you. And then at Ebb headquarters to really do performance testing of those systems. That's where really the engineering is happening. And so we've done that, and now we're in this stage at the Pacific Northwest National Lab where we have that system installed at PNNL, and we're testing it. We have seawater coming into that lab. We're testing it on that real seawater, and also doing some mesocosm tests on organisms to prove safety, and also MRV, so to understand what measurements we need to make for MRV. So nothing we're doing there yet is in open water. We're trying to really kind of lay the groundwork first and hope to have our first a commercial system operating by the end of this year. So here's a picture of Tyson working on that system at Pacific Northwest. And where this is basically halfway between Seattle and Vancouver. It's a Department of Energy lab. I think it's their only marine facility. And it's a partnership between PNNL, which is Department of Energy, PMEL, and NOAA, who are working with they're experts in measuring carbonate chemistry of seawater. And so we're working with them on the measurement verification, and the Salish Sea Modeling Center at University of Washington. So they have very, very high resolution model of Puget Sound in the area. And so as part of this project, they're actually increasing the resolution of that model right near where the lab is in anticipation of, you know, if you would do an ocean alkalinity enhancement deployment there, what would that look like? So with that project, which my collaborator Brendan had the great acronym EASE-OA, electrochemical acid sequestration to ease ocean acidification. We'll answer questions around efficiency and kinetics, MRV, impact on marine organisms, the spatial and temporal timescales we need to think about if we want to do OA mitigation locally, and then precipitation thresholds and ecosystem response. And then finally, one thing I didn't mention, we are always assuming in our techno-economics that we're running 50% of the time, 50% capacity factor. And so this electrochemical system, we can turn the current on and off in tens of seconds. And so this allows us to provide grid flexibility. And so if we are talking to a renewable energy provider about the price of renewable energy, providing grid flexibility in that way allows us to get a good rate for renewable electricity, and also kind of shortcuts the argument. Yes, this requires electricity, but if we provide grid flexibility, it could actually enable build out of renewables. Because you will, for any kind of carbon dioxide removal that uses electricity, you will hear the argument, we should use those electrons to take a coal plant offline first. Absolutely, we should, but we need to be building these things to get ready for when we need these as well. Here's a picture of the system inside PNNL. That's that same 100 ton per year system. And then here's some of the energy data. So we're typically operating at about 50 milliamp per centimeter squared. And this is per net ton of CO2. So this is megawatt hour per net ton after we subtract off emissions from electricity usage. And you can see, so first of all, higher brine concentration, better for us. So we'd much rather get reverse osmosis concentrate from a desal plant, because that concentration is doing some of the chemical potential. That chemical potential is doing some of the work for us. But yeah, these are, we have a path to push these down in the future, but for right now, these numbers are quite good for us. Kind of like we were talking about, a little less than DAC.
Today's grid.
Yeah, so this is using Pacific Northwest grid. So actually, next questions, you guys are amazing. This is perfect timing again. So that is assuming we're plugging into Pacific Northwest grid, which is a lot of hydro. And so that's that Bonneville balancing authority. So this is basically just saying, imagine we're at 1.7 megawatt per ton energy consumption. If we use Pacific Northwest grid, we emit 12% of what we capture, which is sort of at you don't want to be much higher than that. If we use wind only, then we emit 2% of what we capture, which would be quite good. You definitely would not run this or DAC or any such thing that is electricity intensive negative emissions off of average US grid or fossil fuel or anything like that. That would make no sense. Okay, and then so last couple of slides, we're not quite done yet, but we're painting the climate stripes on the EB headquarters. So partially complete. Hopefully we can make the red less red. And this is our CEO and his daughters and another co-founder hard at work. So these are these stripes you see everywhere, charting the global average temperature from 1850 to today on a false color. Yeah. Great. And with that, happy to take more questions, and thanks for your attention.
No question.
So that 0.1% was running around. I missed that. So you're saying that all CO2 removal needed by 2050 would only raise CO2 in the ocean by 0.1%.
No, dissolved inorganic carbon.
Dissolved inorganic.
Yeah.
Okay.
So just take all this, let's see, let me go to that slide.
I missed that. Yeah, sorry. I missed.
It's some number of gigatons, and if you just convert that and compare that to the DIC in the global ocean, so it's a little bit of a, like, you'd be doing it in a specific location. So, but if you equally distributed it everywhere, including the deep ocean, then it's 0.1%. And you could do the same question for surface ocean, and then it's probably like 1%.
Where do you hope to be with AB like 10 years from now in terms of annual gigaton removal? What's your dream?
Yeah, I mean, we have a path. You have to have a path to gigatons that's realistic.
Yeah.
But then you have to ask about the constraints. I would say if we can get to even megaton scale in like 5 years, that would be exciting. But these are all like huge numbers for sure. So I think it's easier to set some constraints on scale. So you could say, what if we took all of the brine being discharged from desal plants today? That's about 100 million cubic meters per day. And you converted half of that to alkalinity, and you assume the 0.8 moles of CO2 per mole of alkalinity, you get something like close to a gigaton, it's like 800 megatons or something.
Okay.
So that's actually encouraging because desal is growing, so you could do that. But then you can say, well, given current permits, actually, you couldn't just put all that alkalinity out of those existing pipes because it would raise the local pH a little bit too much. So you need some new dispersal mechanisms. And so there's a paper that came out recently, Mike Tyka, that we're talking about his other paper, where they model if you did OAE on the coast and limited the pH change to just plus 0.2 units or something, and showing, okay, you can get to gigatons in that case.
Okay.
Just one last constraint, you can ask about membranes, right? So in that case, you would need to scale current ion exchange membrane production to where RO membrane production is today.
Oh,
So all of these things are daunting and challenging, but like doable. Yeah.
So really fascinating talk, but it was actually not what I was expecting because it seems to me surprising that you were not using the cations in this process, the ocean cations, because it seems to me what I thought this was going to be about was like electrodeposition. So like if you had a alkaline environment with lots of carbon dioxide and you had calcium and sodium ions around, I think by applying a little bit of a overpotential and you do like electrodeposition, you would get calcium carbonate, and that would be carbon sequestration too, I think. Do you have any, is that possible, or is there a reason why that logic wouldn't make sense?
Yeah, so you can, I didn't talk about it, but there's a third, I had that slide where I showed OAE and IOC, right? And in the IOC case, let me find it. Oh yeah, this is a better way, 1 second. Here we go. So here we added the acid first, and that shifted carbonate toward dissolved CO2, and you strip it out. And actually in that same paper, we talked about doing the opposite, where you basically add the base first and you precipitate out calcium carbonate. You can do that. There are some reasons when you precipitate calcium carbonate, this is a tricky question. If you precipitate calcium carbonate and you keep it in a basic environment, you're okay. But generally that will release dissolved CO2.
Go back into the ocean.
Yeah. So your efficiency is decreased by half. So the precipitation of calcium carbonate will release CO2 into the ocean. If you're in a basic environment, that can be brought into the bicarbonate state. So it's not like you're emitting it to the air, but you're still decreasing your efficiency by half. But there are some of the CDR companies are basically doing that approach.
Another thought that I had is once you return the system to the ocean and the ocean has an excess alkalinity, my feeling is that for long-term sequestration, what happens is like bioorganisms turn it into calcium carbonate by corals or whatever, shells or so on and so forth. So I'm kind of curious if you know about how fast do organisms produce calcium carbonate as a function of the pH in the ocean? Do they do it faster when it's higher pH, or?
Yeah, that's a great question. So to some degree, yes. And the ultimate fate, like once it gets into bicarbonate, we're good in terms of stability because that excess alkalinity has a lifetime about 10,000 years in the ocean, but that lifetime includes precipitation as calcium carbonate and so on. Actually, one related thing that we need to think about and correct for is there was a paper recently showing that so natural sediments release natural alkalinity at some rate. And if we are doing OAE and increasing omega, the saturation state, it decreases that rate at which sediments release alkalinity. And so you actually have to apply that correction factor, which is about 10%. So instead of 0.85, it goes to actually like 0.75. So there are definitely ecosystem feedbacks and interactions that we need to think about. Yeah.
That's all the time we have. Let's thank Matthew again for this.